In this video, I will show you how to solve vector word problems. It's going to be pretty exciting. A boat is moving in calm water at a speed of 48 miles per hour at a direction of south 26 degrees east. It encounters a 14 mile per hour wind at a direction of north 84 degrees west. Find the resultant speed and direction of the boat. Round to the nearest tenth and make a chart. Well, what's this chart I'm talking about? This is the chart that I am talking about. So we will have a column for each vector. So looks like we have the water and the wind. Well, no, okay, so a boat is moving in calm water. So we've got the boat vector, and then we've got the wind. And then we will have the resultant vector. Now, as far as the rows, in the top row, we will do the magnitude and direction. All right, r and theta. R is the magnitude, theta is the direction. In the second row, we will describe the vectors in component form. Change in x and change in y. So let's see. The boat is moving in calm water at a speed of 48 miles per hour. Well, that's the magnitude right there. So let's go ahead and write that down. 48 miles per hour. Okay. Now for the direction. They gave us the direction as south 26 degrees east. When we say the boat is moving at a direction south 26 degrees east, it means start off directly south and then move 26 degrees towards the east, like this. That's going to put the vector here, where this angle is 26 degrees. Now, we could easily find the reference angle. Actually, never mind the reference angle. The direction that we need for the chart has to be measured from the positive x-axis. So this south 26 degrees east business is not going to work for us. We need to know how many degrees it is, starting from the positive x-axis and then going clockwise from there. All right, all the way to the vector. So hopefully you can see that what I've drawn so far is 270 degrees. So the full angle is going to be 270 degrees plus the extra 26 degrees. So that's the direction. The theta is 270 plus the 26. So theta is going to equal 296 degrees. That's the direction that we need. Okay, so 296 degrees. So magnitude and direction. How about the wind? What did they say about the wind? 14 mile per hour wind. Well, that is the magnitude. So 14 miles per hour. Now how about the direction? At a direction of north 84 degrees west. Okay, so north 84 degrees west. That means start off due north and turn 84 degrees towards the west. So that means the vector is going to be here, where this is 84 degrees. But what we need is the direction as measured from the positive x-axis. We need this angle for the chart. This is the angle theta. And hopefully you can see that theta is going to equal 90 degrees, all right, because right here, as I reached the positive y-axis. That's 90 degrees so far, and then plus the extra 84 degrees. So that's going to be 174 degrees. So that is the direction that we need for the chart. Alright, so now that we've got the magnitude and direction of each vector, we need to turn this into component form for each vector. And the way you do that is by using the formula r cosine theta, comma, r sine theta. That's how you convert from r comma theta to component form. So that's what I'm going to do right here. I'm going to have, remember that r is the magnitude and theta is the direction. So this is r and this is theta. So r cosine theta for the boat will be 48 cosine 296. R sine theta will be 48 sine 296. And you just put this in your calculator. I got 21.04 comma negative 43.14. So let's do the same thing for the wind. Again, we're going to do r cosine theta comma r sine theta. So that's going to be 14 cosine 174 and then 14 sine 174. And just put that in your calculator. I'm getting negative 13.92 and 1.42 from the calculator. So next we're going to find the resultant vector of these two vectors. In component form, that's really easy. And this is the reason why we converted to component form, is because if we want the resultant, all we need to do is add the corresponding parts. So we will add the two horizontal components and we will add the two vertical components, and that will give us the component form of the resultant vector that we're looking for. So I'm just going to do that in my calculator. I'm getting 7.12 comma negative 41.68. So now we need to take this component form for the resultant vector, and finally we need to figure out the magnitude and direction of the resultant vector. We need to find this version of the resultant vector. So let's just do that off to the side. If I want to find the magnitude, I will simply use the magnitude formula. Okay, so looking at the component form, I'm going to take that and I will do 7.12 squared plus negative 41.68 squared. And I'll take the square root of all that, and that's going to be the magnitude. So I'm getting 42.3, and that is miles per hour. So that's the magnitude. So now we need the direction. So here's what we do. Let's take the component form and figure out what quadrant we're going to be in first of all. See how the horizontal component is positive and the vertical component is negative? That means we're going to go to the right and down, or east and south. So that's going to definitely put us in the fourth quadrant. So let's just draw ourselves a vector into the fourth quadrant. And then go ahead and make a triangle out of it so we can do our analysis. And it will be helpful to know what the reference angle is. Alright, this is the reference angle, the angle between the vector and the x-axis. Considering that we drew this triangle by going right 7.12, so this side is 7.12, and down 41.68, so this side is negative 41.68, but I'm really going to ignore the negative sign because I just want the positive value of this reference angle. I can calculate the direction this way. Alright, I'm going to start off by finding the reference angle using the tangent function. The tangent of the reference angle, that's opposite over adjacent. So that's going to be 41.68 over 7.12. Again, I'm ignoring the negative sign because I just want a positive r. So that means the reference angle should equal the inverse tangent of 41.68 over 7.12. So just put that in your calculator. So the reference angle turns out to be 80.31 degrees. Now we have to be careful about how we describe the direction. We've learned three different ways of describing direction. Measuring from the positive x-axis all the way around. That's what we've been using on the chart so far. There's also something called bearing, where you measure from the positive y-axis clockwise. But then there's the way that the direction was given in the original problem. Remember how the first vector direction was given as south 26 degrees east, and the second vector was north 84 degrees west. Well, in your final answer, you need to give the direction using the same format, the same type of direction that was used in the problem, in the original problem. So we need to write a direction like these. Well, since we have the reference angle anyway, we might as well use it. So let's see. We could think of this position as starting from the east. So I'm going to say east. And then we can think of this as moving r degrees towards the south. And r was, of course, 80.31. So we started at east, and then we turned 80.31 degrees in the direction of the south. Okay, so we started at east and we turned 80.31 degrees towards the south. So this is how you would write this direction using this type of format. So I just went ahead and recorded the information on my chart. For my final answer, maybe you've noticed that I was using 2 decimal places throughout the problem, but then in my final answer I only put 1 decimal place, and that's because they said round to the nearest tenth. But I like to wait till the end to round to that last decimal place so that my answers are a little bit more accurate. So again, this is the resulting speed and direction of the boat after it's being affected by the wind. Let's do one more problem. A plane traveling at 660 miles per hour is flying with a bearing of 130 degrees. There is a wind of 70 miles per hour blowing south. If no correction is made for the wind, what are the final bearing and ground speed of the plane? Well, once again, we're going to make this chart. We're going to have a vector for the plane, and we're going to have a vector for the wind. And then we will have the resultant vector. Alright, and that's what we were being asked to find, the actual speed of the plane after it is being affected by the wind. So it's the combination of the plane speed and the wind speed will determine the actual path of the plane. So, like we did before, in the first row we will record the vector using the magnitude and the direction. In the second row we will convert to component form. Let's start with the plane, magnitude, and direction. The plane is traveling at 660 miles per hour. That is the magnitude R. So 660 miles per hour. There's your magnitude. Now, for the direction, they're giving the direction as a bearing of 130 degrees. Okay, let's write that down. Bearing 130 degrees. Now, bearing is a way of measuring direction where you start from the positive y-axis. You start from north and you measure clockwise from there. So a bearing of 130 degrees, what quadrant is that going to be in? So if I start going clockwise, there's 90 degrees so far. If I went to here, that would be 180 degrees. That would be too far. So I know that I am dealing with an angle that is going to be in the fourth quadrant. So I'm just going to go ahead and draw this angle into the fourth quadrant. Okay, so this is an illustration of a bearing of 130 degrees. But what we need is the angle that is measured from the positive x-axis. So we need to know this angle that I'm drawing right now. Alright, for the chart. And we're going to call this angle theta. And when we talk about magnitude and direction, this theta always has to be measured from the positive x-axis. So what is that? What am I going to do? Let's find another number. Let's figure out what the reference angle is right here. So hopefully you can see that this reference angle should be the 130 degrees that we got from the bearing minus the 90 degrees that we started with. Alright? Because 90 degrees plus the reference angle, that's the total 130. Alright, so this turns out to be 40 degrees. And again, I just found that by doing 130 minus this 90. So we found the reference angle. Okay, once you have the reference angle, it's going to be much easier to figure out the direction angle theta. Because hopefully you can see that theta was on its way to being 360 degrees, but then it had to stop short by 40 degrees. So in other words, theta is 360 degrees minus the 40 degrees that it didn't quite go. So that means that theta is going to be 320 degrees. And that's the angle that goes on the chart. Alright, that's the direction theta. So 320 degrees. Let's do the same thing for the wind. There's a wind at 70 miles per hour blowing south. So 70 miles per hour, that's the magnitude. Now the direction is given as south. Okay, so it's just south. Simple. They didn't say bearing or anything like that. They just said south. So that means that the wind is blowing right here. But again, we need to record the direction as an angle measured from the positive x-axis. So we need this angle, theta. And hopefully you can see that theta is simply 270 degrees. Alright, so that's what needs to go on the chart. Alright, and we would love to write the magnitude and direction of the resultant vector because that's the final answer. But unfortunately, there's no way to directly combine the magnitude and direction when you have the magnitude and angle like this. So we need to take a pit stop and translate the magnitude and direction into component form. And then it will be easy to calculate the resultant vector. So the way you find the component form is you use this little formula, r cosine theta for the horizontal component, and r sine theta for the vertical component. And this is r and this is theta. So for the plane, that's going to be 660 cosine 320, comma 660 sine 320. Just put that in your calculator. Alright, so the plane vector in component form is 505.59, comma, negative 424.24. Let's do the same thing for the wind. Again, we can convert from magnitude and direction to component form using the little formula r cosine theta, comma, r sine theta. So for the wind, that's going to be 70 cosine 270, comma, 70 sine 270. Just put that in your calculator. As soon as I went to type this in my calculator, I felt really silly. Did we really need this formula? Did we really need a calculator to know this? Remember, the wind was blowing due south. So the horizontal component, there is no horizontal component. It's only vertical. So the entire magnitude of 70 miles per hour is in one direction, to the south. So it's all going to be vertical, and it's all going to be negative because it's to the south. If it were to the north, it would be positive 70. Alright, so we didn't really need any calculations to do that. A little bit of common sense. Anyway, we can now easily find the resultant vector in component form by simply adding the corresponding parts of the plane vector and the wind vector. So we'll add the 505.59 with 0, and we will add negative 424.24 and negative 70, and that will give us the resultant vector. Use a calculator. So the resultant vector in component form is this, 505.59, comma, negative 494.24. But we need the magnitude and the direction of the resultant vector, just like we had the magnitude and direction for the plane and the wind separately. So we can get the magnitude from the component form by using the magnitude formula. So we can do 505.59 squared plus negative 494.24 squared. If you're going to include the negative sign, make sure you use parentheses around this. It will mess up your whole answer if you don't use parentheses. You will not get the right answer. Anyway, use your calculator. So I got 707.03. So that's the magnitude. Alright, that is the resulting speed of the plane once you take into account the wind. Now we need the direction. So whenever I do direction, I like to make a diagram. So looking at the component form, notice that the horizontal component is positive and the vertical component is negative. That means I'm going to the right and down, or east and south. Either way you look at it, we are in the fourth quadrant. So let's make a little triangle out of this for our calculations. So this is to the right 505.59, and it is down, so this is negative 494.24. To find the direction, we will need this reference angle. And we can find the reference angle by doing the tangent of angle R, which should be opposite over adjacent. Now I'm going to ignore this negative sign and just do 494.24 over 505.59. I'm ignoring the negative sign because I just want the positive value of R. So if I want to find R, I need to do the inverse tangent of all of this. So put that in your calculator. So I'm getting that the reference angle is 44.35 degrees. So now I need to use that to find the actual direction. Okay, now remember that when they gave us the direction in the problem, they gave us the direction as a bearing. That's important because bearing is one of three ways that we use to describe direction. But for your final answer, you need to describe the direction using the method that they used in the problem. So we've learned about bearing, we've learned how to measure from the positive x-axis, and we've learned to say things like 44 degrees south of east. But for this problem we're going to do bearing because that's what they used in the original problem. So remember that bearing has to be measured from the positive y-axis clockwise. So we are looking for this angle that goes like this. So I'm hoping that you can see that this bearing, alright, and there's no symbol for it, so you have to use the word bearing. This bearing is going to be 90 degrees plus this reference angle. From north to east, that was 90 degrees so far, plus the reference angle, which is 44.35 degrees. Add those up, and that's going to be the bearing. So this is going to be 134.35 degrees. So I'm just going to go ahead and write that up here. And this is really the final answer. This is the magnitude and direction of the resultant vector when you combine the motion of the plane and the speed of the wind. So your final answer might look like this. Speed is 707 miles per hour, bearing 134.4 degrees. Alright guys, that's going to do it for this video. Go ahead and click here in the red apple to watch the next video. Click in the green apple to subscribe, or click the yellow apple for the full playlist.